This episode we are going to build a synthesizer controlled by the sensors on the smartphone, and that would be a typical like a subtractive synthesizer, like an analogy one, but it's of course all digital. And I think we start off with playing on it. I point to the right, I init the sensors, and then I explore. Okay, so we have pitch, we have volume, and timbre connected to three different axes on the device. So we have pitch on the alpha, gain on the gamma, and timbre on the beta axis. So now let's look at the code to see how it works. To start with, we need to build the synthesizer itself. And to build a synthesizer, a super simple one, we need an oscillator that can make frequencies using a waveform. And this oscillator node is now set to sawtooth. That's a typical synthesizer waveform with a lot of harmonics, so we get an interesting timbre to play with. The sine wave in the last episode doesn't have any harmonics, so we don't have like any chance to do the wow wow timbre aspect of the sound. So I'll start with sawtooth. There are various different waveforms. The most common are a sine, sawtooth, and square. There's also a triangle. All right, the sound of the oscillator needs to be routed to, or is it routed? Routed to a filter. So now you should imagine these three elements as being something like a modular synthesizer, or like a guitar effect pedal board. So we have different audio objects that are connected to each other. So the output of this element is outputted to the next element. And the output of this one goes into this one. And finally, that one goes to our ears or the speaker. So how is that done? Well, the oscillator plays a sawtooth and the output is set to next. And next means to the next element on the next row. That will be the biquad filter node. And the filter deals with the harmonics. So it can do this wow, wow, wow effect. If it's a low pass filter, and that is a default filter we are using for this example. There are several other types you can use as well. You can Google the biquad filter node and read more about it. All right, and the output of the filter is connected to the next element, which is a gain node, which is more or less like a volume controller, actually. And finally, the output from the gain node is then going to the audio output of the computer or the smartphone. It's important to understand that the output is from this one is the sound of the oscillator with all the harmonics. The output of the filter will be the result of the filter manipulating the sound from the oscillator in real time. And the output of the gain node will be the result of whatever was put into the gain node, which is the sound from the filter, manipulated with the gain on the gain node. So that means that we have three different access points to control the audio. And that will be the pitch on the oscillator, the frequency of the oscillator, the frequency of the filter that does this wow wow thing, and finally the gain of the gain node, which is the ha ha volume. Okay, so 3 different variables needs to be introduced here. And I decided to go for P, F, and G as the names. And to set them up, I use 3 variable elements at the top. And this is how I normally do it. I put the variables at the top and then I do the elements and build the audio construction beneath it. So I give them appropriate names, P, F, and G, and I connect them to the different orientation variables accordingly. So P is connected to alpha, F is connected to gamma, and G is connected to beta. And then the interesting things happen with the mapping. And I think we start with the easiest one, the gain. So when I initialize the sensors on the app, I will get values from, I think it is minus 180, which is like all the way down, I think. I'm not quite sure now. Maybe it's backwards to plus 180. And I just happen to want to have the values between 0 and 60. So 60 I want to be quiet, and 0 I want to have maximum volume. And then we need to know that gain on the gain node goes from 0 to 1, which is 0 is quiet and 1 is maximum volume. You can have higher volume if you would like to, but let's stop with 1 at the moment. Otherwise you get distortion. So then I map 0 on the beta axis to output number 1. So we get maximum volume when the angle is 0. And then when the angle is 60, I want it quiet. So then I map it to 0. And the mapping process will interpolate between those 0 and 1, depending on the angle of the beta axis. Similar with the gamma, that was the timbre. So I want to pick up values between 0 and 90 on the gamma axis. And I map them to 200 and 2000. So if the angle is 0, the output will be 200. And if the angle is 90, the output will be 2000. And anything in between if the angle is in between. All right, this relates to the frequency of the bicorde filter node. So that means that this will generate a filter cutoff frequency on 200 Hertz, and this will map it to 2000 Hertz. So it will be the wow effect. Finally, we talk about the alpha, controlling the pitch. I chose to have 90 to 270 degrees that I'm interested in using, which is fine. If I point towards myself in its sensors, then I get the playable area towards the screen. In this case, I map it to a series of numbers here. And if you're into music production, you might recognize those numbers. They are MIDI note numbers. And you can Google that and see what that is. But that is basically just a numbering of the keys on a piano from like a super low note to a super high one. And 60 happens to be the middle C. So if the angle is, I think it's there, 90, then the output will be 60. If the input value is 270 degrees, the output will be 72. And in between those values, it won't interpolate this time because I have set the curve to go in steps. So it will rather pick values from this list of values. And these values are now numbered keys on the piano, which means that if you take one step up, that will be one semitone up. So if this is C, then 61 would be C sharp. 62 will be a D. 64 would be an E. 65 an F. G, A, B, and then the next C, which is 12 semitones higher than the lowest one. So the result is actually da 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 da, a C major scale. That moves in steps when I do this. But this is not the range of values that is appropriate to set the frequency of an oscillator. The oscillator does not know about like piano keys and stuff like that. So we need to convert the numbers in the world of piano keys into the world of frequencies. And there's a built-in feature in WebAudio to do that. And you just add this attribute, convert equals, and then type exactly as I've done here, MIDI, and then an arrow frequency. So MIDI dash greater than frequency is an indication that it takes the MIDI note numbers and convert it to the frequency matching that MIDI note number. There are lists online as well, so you can look up those frequencies if you'd rather enter different frequencies here and skip this conversion. It's fine, but this is quite handy, so you might like it. All right, so let's just try it again. Sorry, I should point toward myself when I'm in it. So it moves in steps, turns off the volume when I move it upwards towards 60 degrees, and it changes the timbre when I move it on the beta axis. So it actually works. So now let's just quickly try and see what we can do with the pitches to do something clever. For example, we could do sorry, should be 63, which is a minor third. Do, la, a minor sixth, and a minor 7. Save it and reload the page. Hit the init sensors, and now it's minor. And if you're into quarter note steps, no, it's not quarter note. Anyway, like detuned stuff, you could do like 63.5 and save it. Then you get like a third, which is between major and minor. So you could actually make up any scale, but by just entering numbers. Remember that you separate the numbers with comma sign, and you can do the decimals with a point.